before I go. Oh my gosh. Here we go. I think we're finally figuring it out. We'll see. My only KPI for the year is don't get fired, and I'm not on track to hit it at this point. Okay, here we go. Let's not show Slack. Let's find where we're supposed to be. Okay, great. On Restream? I was. Did it stop? Okay. Hold, please. Let's share the screen on Restream. There we go. We good, Victor? Excellent. All right, starting off strong. I appreciate everybody coming here. Very cool about Fresho holding the regular meetups at their office. I remember years ago trying to start off some of the Apache Iceberg meetups in Seattle and San Francisco, and nobody wanted to come. I was begging people to come talk about Iceberg, and they're like, stop knocking on my door, go away. And the only people who came were the Snowflake people because it was at their office and they had to. And now the most recent San Francisco meetup was hundreds of people. We had to get a special permission from Apache to hold a meetup of that size. So Iceberg adoption is growing like crazy, and it's so great to see. When I started in data, the very first tool that they had me learn was SAS. And I was like, well, there's this thing called Python and even R, but why aren't we using that for predictive learning? They're like, oh, open source tools are not trustworthy. We can't verify them. And now, thankfully, open source has become business critical. So not just a nice to have, not just a way to save money, but it's becoming business critical, and especially with things like AI. And we'll talk a little bit about that. So JP's not going to push Dremio, so I will push it for him. So I'm one of the co-authors on the Apache Iceberg book back when I worked at Dremio. And so if you want a free copy, please get a free copy of that book. Jeff Bezos doesn't need your money, so please download it from free and take Dremio's money. That would be great. I've got 2 more books coming out. I'll get you free copies of those. So I've got an early release of the data transformation, the definitive guide that I wrote for O'Reilly. 2 weeks out, early release there. And then AI Ready Data, I'll get you a QR code for that. Just got the final manuscript submitted today to Wiley. Okay, so why should you listen to me? You probably shouldn't, but here's a little bit about myself. So currently head of DevRel at Fivetran. Before that, I was head of DevRel at Tobacco Data, and Fivetran acquired our company, which is why I'm there. And we're the creators of the open source tools SQL Mesh and SQL Glot, if you've used any of those projects. Before that, I was the field chief data officer and working in evangelism at Dremio. But before that, I had a real job where I led data at a bunch of different places. So I know what it's like hands-on. I teach graduate courses and a bunch of different data things. But none of that matters because I just got my silver play button on YouTube. So now this is my final talk, and I'll be retiring as an influencer. Yeah, good laughs. I'm glad this is going really well. They're like, your presentation's a joke. Get off. Anyway, so a little bit about Fivetran. So why is Fivetran even at an Iceberg meetup? Because we're all in on open source and particularly Iceberg. So with Fivetran, you can move data from anywhere to anywhere, including Iceberg. So that's a little bit about that. So let's get started. And I usually have a different talk I give, but Victor keeps putting me first. And I think I know why. And it's because, you know, like when you go to a comedy show, how there's an opener who's not very good, and it's like the warm up, and if he does bad, you don't super care. I'm the opener, and now I see why Victor does this. So because I'm going first, I would just want to set the stage a little bit with Iceberg. So who's currently working with Iceberg like in production? Heck yeah. How many of you work for Dremio? Just kidding. Yeah. All right. So really, so all of you are using it in production. That's fantastic. What are some of the companies you work for? Shout them out. Oh, good. Good company. Tower? Yeah. Heck yeah. Tower.dev? Yep. Yeah, the Tower homies. Fantastic. You guys just hired Marissa. We did. Heck yeah. Good call. Marissa's great. What other companies? Fresha, yeah.
Obviously.
Fresha, awesome. Any other companies using Iceberg? It's confidential. Okay, pearls before swine, all that kind of stuff. Like, you got to earn us telling you where we work. Okay, great. Glad this is going super well. Okay, so let's go back into the history a little bit of how we got here, because from my perspective of leading data, I was still leading data when ChatGPT 3.5 rolled out, and then subsequently 4. That's really where a lot of these AI initiatives came down. And I mean generative AI, not traditional AI like deep learning. And it was a board down directive to, hey, do AI. And I was like, oh no, what does that mean? And they're like, figure it out. And then I looked at our data infrastructure and I was like, oh no, how am I going to do AI on top of this? And that's, as I go around and I consult with companies about, hey, one, do you want an AI strategy or not? That's a whole other thing. And then what are the challenges with implementing on top of your existing infrastructure? And it's a nightmare. And we'll talk a little bit about why that is. So if we look at like the history of data storage, so if you go back to like the 1950s, back in the 50s, really the entire purpose of data was really just to power like an application, and it was all embedded inside there. So the application and the data and the metadata and the storage, it's all just one thing, completely locked together. And that really continued until like the 1960s, when finally this concept of a database was extracted from the application, and the entire purpose of that database really was just to provide operational support and power those applications. Business critical, we need to make money, that comes from the application. And inside there, you really had to understand exactly how the data was stored in order to access the data. And this was a challenge because it was difficult to understand exactly how the data was stored, it's difficult to access. And inside, it didn't really talk to each other. So in the 70s, like in 1972, E.F. Codd rolls out his paper on relational databases. And there's a few things that are awesome about that. One, suddenly now we have this concept of a logical schema. So we can describe the data, the metadata, without exactly having to know exactly what's stored, so that we can query it and get business value from it. And so we start getting this concept of relational databases to power an application. Still business critical, it's row-based, we just need to power the app. But because it's a relational database now, we can power multiple applications with the same database. So now we're using our technology more efficiently, we can power more applications with just using the same database, but you can't use multiple databases on the same application. They just don't talk to each other, but it's a step in the right direction. So 1970s, bad for clothes, good for data. So in the good, appreciate the snicker up front. Tower.dev's got me. Then in the 1980s, so right now, this is all transactional, right? This is all just powering the application. And so we really only have this concept of transactional data. But in the 1980s, something awesome happens. And it wasn't in Miami. So we've got Bill I love Tower.dev, he's got me, man. He's got the Snickers. So in the 1980s, Bill Inman and then some other folks at IBM are thinking, oh, we've got all of this data in these databases powering these different applications, which is great, business critical, we're getting business value out of them. But what if we could get one source of truth? So this database doesn't talk to this database, doesn't talk to this database. What if we could centralize that into this thing we'll call a data warehouse, and then we could do this new thing called analytics. And we could start trying to get value out of the data beyond the applications that they're powering. So a couple things had to happen in order to make that possible. So all of these applications and databases, right, we had to figure out some way to get the data into this warehouse. So this is where your friend and mine, ETL, had to be invented. And really IBM kind of invented it, but Bill Inman was involved. Ralph Kimball was involved in learning about warehouses and marts, but now suddenly we can kind of centralize our data and we've got this new concept of data modeling inside of this warehouse, where now we can do a lot of reading and we can try to get value out of this aggregated data beyond the value that we're already getting from powering our business applications. And this is important because up to this point, it's all been transactional, but with general architecture rules, we've got this kind of split between OLTP, transactional, and OLAP. And this is the first time, online analytical processing. And this is the first time that this really happens. This is us acknowledging that up to this point, it's really just been transactional. We really need it fast and low latency and interactive, but that there's value in the size of data. So with like the data value continuum, with a lower amount of data up to a higher amount of data, there's different things you can do and there's different value, right? So up as the data grows, we need a different type of system to deal with the aggregations there, but also the amount of time also increases. So OLTP is really dealing with very short time frames, and OLAP can go, much longer. So we're starting to realize like, oh, there's different use cases and we need to build different systems in order to meet those use cases. So this is the first time that OLAP really becomes possible and rolls out. But we can't mess with the business critical applications. That's what's making us money, right? So we need to, we need to move it. Okay, thank you very much. Put JB on the stage. That's what that signal is. We'll try this. Oh, did it time out? That's what it is. Lectern. There we go. Awesome. So now we're acknowledging different use cases need different types of systems. And up to this point, still everything is tightly coupled together. So yes, we were able to get the database out of the application, but inside that database, we're still dealing with compute is coupled with metadata, which is coupled with data, which is coupled with storage. Even in those early warehouses, everything is still coupled together, and you can't scale independently. If you need more storage, you get more compute. Your data is written in a proprietary format, and the metadata is tightly coupled with that data. You can't separate any of those. So it's working as a tightly controlled system, but we run into scaling issues. So in the 1990s, we start to see some compromises there, because up to this point, really, in the 80s, we really just start dealing with the types of data volume where we start needing OLAP, but it really didn't come to a head until the 90s, where we start having more data. And so we make some compromises. We start getting MPP systems like Vertica, right, where they are now trying to scale horizontally across nodes, because we're dealing with databases that just have so much more data. And then with the OLAP systems, Ralph Kimball says, hey, I know that your big idea was get a single source of truth in this warehouse, but nobody actually is doing that, because sales is like, hey, we don't want to dig through all of the data from marketing, so we're going to set up our own warehouse. And then marketing's like, well, we want our own warehouse, and HR's like, we have special data, so we want our own warehouse. And so now you've got all these silos. So what was supposed to be a single source of truth has now become a bunch of different silos. So Ralph Kimball in the 90s like, okay, let's just pretend like we're not trying to get a single source of truth. We're just going to create data marts, and we're going to do dimensional modeling, which is really query optimized, and we're just going to plan that every business unit has their own specialized OLAP store. So we start making those compromises in the 90s, where on the OLTP side, we've got massive parallel processing. On the OLAP side, we start just doing smaller, more specialized data marts. We're just pretending like there isn't a single source of truth. And that's really where we are at in a lot of systems, because we're not really getting rid of much. We still need OLTP systems, and we're adding on warehouses. And we didn't really get rid of warehouses. We just added on more data marts. And so our data storage landscape just starts to really sprawl. And we get silos, they don't talk to each other. And it becomes even more compounded in the 2000s, because now instead of just rows and columns, now we've got the internet, which is now dropping tons of unstructured data on us. And so in 2006, we get two different solutions. We get S3 and Hadoop, HDFS, both drop in 2006, the same year. And S3 was really awesome because now, we've got our data lake and we can drop all of this unstructured data in here. And we can access it by HTTP. And so this is awesome because this is the first time that we truly decoupled storage from everything else. So in S3 Object Store, now we've got storage completely separated, but our compute is still really locking up our metadata and our data. So all of our compute engines, even writing to S3, are still writing really kind of in a proprietary way. And so to read it, you need that specific engine. But at least we've decoupled storage. So if you can access HTTP, you can access S3. Storage now can scale elastically because it's in the cloud. So you can just grow your S3 and storage becomes quote unquote cheap, which becomes an economic incentive to maybe make compute a little more expensive. If companies are maybe not making so much money on storage, maybe they're going to make more money on compute. And so that's important because now we can scale elastically. But our compute, even though separated from storage, is still locking up our data and our metadata. And this is really true until the 2010s, when a couple things happen. So in like 2013, we get Parquet. And Parquet is important because now we can separate data from a proprietary format into something open that multiple engines could read. So Parquet makes it possible in 2013. So now if we're using S3 as the example, now we can have our storage separated, our data separated, but our compute is still kind of locking up our metadata. And there's some other things that happen around that time. So shortly afterwards, like Snowflake goes GA in 2014. And so Snowflake is awesome at this time because what they're doing is they're taking advantage of the elastic scaling of the cloud, and you can spin up warehouses of different sizes, and they are embracing the separated compute, but it's still in a proprietary format. So even though you're able to do like columnar storage inside of a cloud data warehouse at that time, it's still being stored in a proprietary data format, so you can't really pull that data out. If you want to move that data, you need to do a full migration to whatever you're going to move it into. But at least we are embracing the full separation of storage and compute at that time and taking advantage of that. So this is where we're living when Iceberg comes out. So to this point, we've still continued to expand our data landscape. We still have all of these transactional systems. The need for OLTP didn't go away. We still have our OLAP systems kind of siloed and spread all over the place. We probably have multiple warehouses, different business units, or maybe spinning up data marts for different business use cases. And we've added a data lake, and we're just dumping tons of storage into our data lake, which is difficult to govern. There's really no schema enforcement, something that Victor may address later. And then we move to cloud data warehouses, which is great, but we're still using proprietary formats and proprietary compute. So we've solved some things, but we've created some other problems there if we're really trying to just find full interoperable freedom and avoid vendor lock-in. So we're doing okay, but really we've really just expanded our data landscape. And this is really where a lot of enterprises sit and what they look like as they're trying to do like their AI strategy. They're like, do AI. They're like, have you seen what our data architecture looks like, what our infrastructure looks like? Well, we don't have a single source of truth. We don't even know who has access to our data lake. Delete that column. Did it really get deleted? Maybe, maybe not. And so in 2017, 2018, this is really where open table formats come in, where Ryan Blue, with his other co-inventors of Apache Iceberg, they really want to use a lot of the data inside of their data lake, but they don't want to give up the ACID transactions, but also moving it into a cloud data warehouse and only accessing it from there can be cost prohibitive. So there has to be a better way. And this is really where Iceberg and other open table formats come in, where suddenly all of these files that are scattered throughout the data lake, we can organize them and create a logical model of a table, and we can just access it that way. So this is huge, because now suddenly we have all these benefits of the cloud data warehouse, but without that proprietary vendor lock-in. And there can definitely be benefits to using a proprietary vendor tool, but if we want to avoid it, what the data lakehouse enables is that now we've got our storage, like if we're storing that in S3, our storage is now separate from our data, which can be something like Parquet or C. And now our metadata can be free through things like Iceberg, where we're saying, okay, our metadata is just files, and we can access those files separately from the data. And we can use whatever compute engine we want that's compatible. We can use DuckDB for ad hoc queries. We can use Trino. We can use proprietary things like Dremio or whatever we want to use. It's our choice. So now we've got all of the benefits that we were looking for, but it's completely interoperable and can avoid vendor lock-in if we like that. So why am I excited about that? So when companies are considering their AI strategy, it's different than the other use cases that we've come up against, because with thinking about that quick chart of like, still there. Okay. So if we're using rows versus like aggregations, previously we really could align our infrastructure with specific use cases. If we need low latency, row-based interactivity, awesome. We can get Postgres, we can use things built for that. So the compute storage coupling makes a lot of sense there. So if we need applications, that's good. And then if we needed smaller analytics, we could do things like columnar databases, or we could use a data mart, we could do something like that. So for smaller analytics, but when we really get into large scale data, quote unquote big data, that's really where we need an OLAP system. And it can be super cost prohibitive to dump all of your data into one vendor and then have to use their compute in order to access it. But the challenge is with AI, previously, like if you've got an analyst, they can make the decision over which system that they're trying to access, and they've got the tribal knowledge and all those things. But we're talking about not using an analyst, and we're saying our AI strategy is that AI is going to have access to all of these systems in order to do that. If it's going to reason over your data, well, that's probably going to be a lot of different hits towards multiple systems. The agentic agents who have access to your systems, and there's lots of guardrails policies around how to do this, but as it's reasoning, it's doing multiple queries over your data. And if it's doing that through a proprietary engine, you could potentially rack up a ton of costs. So you want to be able to choose whatever engine you need. But if your data landscape looks like this, where stuff is everywhere, now Iceberg gives us the opportunity to really start consolidating some of this so that we can have stronger governance. So Iceberg is not a transactional database. So we still need something like Postgres. We still need a database for a lot of different use cases. But for analytics and aggregation, we can use a lakehouse with a lot of strong governance. We can centralize things. We can get closer to that single source of truth that Bill Edmond was looking for. But now AI also has another need beyond just transactions and aggregations. It also needs this thing called context. And we can try to provide context through YAML files and call them a semantic layer, but it also needs to generally have graphs. So now we have the need for these graph databases, or we need to, we need to provide, this is great. Here we go. Or if we're doing generative AI, we've got all this unstructured data and we need to provide embedding. So we need things like vectors. And so our AI really spans our full data infrastructure and spans all of these use cases versus these siloed use cases that we've had in the past. And so Apache Iceberg really enables us to, one, be flexible, two, provide interoperability, because we don't really know what our AI use cases are tomorrow. So the more we can avoid vendor lock-in and have interoperability, the more future-proof we can make our infrastructure. So this is why, one, understand a little bit more about where modern enterprises are with their infrastructure and how they got there, and two, what the opportunity is for Apache Iceberg to have significant impact on building out a robust infrastructure that can actually power AI. At NVIDIA GTC recently, Jensen Huang said that structured data is the foundation for AI. What did he say? Is that how it went? Something like that. He said structured data is the ground truth for generative AI. I'll look it up. It's something like that. Don't quote me. And I believe this is why, because it provides generative AI, which is creating things, right? Probabilistic, it's creating things. It needs to ground itself in what is. And in order to ground itself in what is, it needs to have access to your applications in a structured, meaningful way. And Apache Iceberg is a strong core of an AI-ready infrastructure. Thank you.
All right. Do we have a question? Maybe like auction. You have a quite cool painting. Maybe we could just sell it here.
What painting? Oh, this one. Yeah. Yeah. I'm competing with my 3-year-old to see who's the better artist. I expect you all to vote for me.
Thank you, Andrew. It was awesome just to get more insight of it. Oh, we have a question.
Dang it, JB. Come on. I thought we were homies. Yes. I can hear you. Yeah.
On your diagram at the bottom there, your lake house ended, and then you had AI to the right.
Yeah.
Where does Iceberg take us
So,
to the right?
So the way I look at it and what I'm seeing work in the wild is that I believe that the lakehouse should be the center of your data architecture, but it doesn't replace the whole thing. You still need transactional databases, which is why we saw Crunchy Data and we saw Neon get acquired, right? And we see PG Lake roll out and all these things because agents still need that transactional data. That's where the harness lives, all that stuff. Also, semantic layer doesn't fully meet context in my experience. It does not fully ground the agent in truth. So we still need graph databases often. We definitely need vector databases for certain use cases. But I think about it what I call the core and explore. Like if the lakehouse built on Iceberg, right, is the center of your data architecture, that can be your source of truth, and then you branch off of there into certain use cases. So the transactional data can flow into the lakehouse, and then the lakehouse can flow for certain use cases into the graph database and into the vector database. It's easier to build that greenfield, right? It's very hard to go back and move, for instance, from a cloud data warehouse and then backfill everything into a lakehouse. So that's why it's like, let's do this use case by use case specific. I believe ultimately to be fully interoperable and future-proof, Lakehouse should be the center because it does decouple storage data, metadata, and compute, which gives you the ultimate flexibility. Is that helpful? I just talked until I saw your eyes glaze over and then you forgot what your question was, and that's my strategy.
Perfect. Well, again, thank you, and let's give an applause.
Oh, yes. Well, it took forever to get it on. I don't want to give it back.
Okay.
Thank you. Did you get the link?
What link?
For
What link? Mm-hmm.
Are you online?
Mm-hmm. Yes, but I have again to disconnect. 1 second. not this link. In the meantime, we can all have more food because there are 9 minutes left.
9 minutes left to get more food, guys. And I was thinking about the food. I think they just taking care of us, so we're not, getting more on our daily. Yeah.
Okay, which email? Nico Lazar. Oh no, I'm not in. You can send me. No. Just I need the link. You should have gotten. Nico. Where is it? What? Where is that? That.
Wait a second. It's,
No, okay. No. I'm not with K.
Almost German, yeah.
so if you will get it in a second.
Hopefully. Don't receive the email. Yes. Okay. Okay.
Ooh, that was
Right.
hard.
Do you hear me now? Okay. Perfect. So this was the time we needed to get more food. So if you didn't have food now. Okay. So today we will talk again about Iceberg, but this time we will see how we can query it from various clients. We will focus today on Starox, which is one of the newer OLAP data sources. I want to ask first, who of you have heard about Starox in the past? Or uses, or okay, 3, 5, okay, 5 people. Okay, that's fine, we'll learn together. Right, so today we will focus on querying Iceberg and specifically performance considerations, right? Or using Starox as an Iceberg client and how you can use various ways to read data from very simple direct reads, union reads, but also more complex and quite challenging, not yet released, some of the things, using materialized views. That being said, I don't know why I'm doing this because I technically should have this thing. Now, why is challenging to work with Iceberg, specifically to querying? Why any engine has issues to query, right? Where the complexity comes in. The complexity essentially comes from the fact that all these clients need to understand the spec, right? Iceberg is not a database, right? It's just a spec, and it needs the clients to understand the specific spec, right? Of course, there are other issues around the object storage latency. All our files are in storage, all our data is in storage, and we need to understand the data. We need to be able to navigate the metadata, and we need to deal with all sorts of issues around the storage ecosystem, right? File fragmentation, data freshness, and others, right? Oh, why am I moving in the wrong direction? Now, we of course need the mandatory Iceberg recap, the diagram of what Iceberg and how Iceberg looks. So there are two parts of the spec. On one hand, metadata plane that essentially just are pointers toward between metadata files, manifest lists, and manifest files that actually point to the actual data files on the cloud storage. Right. On the other hand, there is the data plane where the data resides. Right. Now.
Can you clear the thing off the bottom of the screen?
Oh, sorry. Okay, 1 second. That should have been hide. If I can click, that's nice. Nice. Okay, more technical issues. Right? Okay, that's fine. So Starox, right? I was mentioning Starox earlier, and why? Because it is a very nice client for Apache Iceberg. It has a deep integration with Iceberg and actually provides some features that not other clients actually support as of yet. Some of them, again, not even released. So what does it mean to query Iceberg and to use Starox as an Iceberg client? Well, as Andrew said earlier, we decided to separate storage and compute, right? So all our queries are actually handled by some front-end nodes that just act as coordinators and plan query planning. And then the data reading and query execution is handled by compute nodes, where data that actually read the data, right, from S3 or from any cloud storage. Now, when a query hits Starox as an Iceberg client, that query will be parsed, and of course, metadata needs to be navigated in order to get to the data. So what does it mean? It means that we need to be able to fetch all those manifest lists, manifest files, and we need to do this in a very performant manner. Now, of course, even if we want to query one single file or one single record, we still need to navigate and to get to the data file where that single record exists. And there might be a lot of these files, these metadata files. Starox optimizes this via an algorithm that they call adaptive retrieval strategy that essentially says, okay, if I have not that many files to read, metadata files to read, then I will just read them locally. I will cache those in my memory, and that's it. But otherwise, I need to divide and conquer, and I need to ask multiple backend nodes to do this reading in parallel. But of course, once I get all this metadata, I will cache heavily, right? Because I want to avoid to get to S3 too often, right? I want to reduce the number of files that I read, and I want to also reduce the number of calls to the S3, right, to cloud storage, right? But once we have the metadata, we can actually start planning and executing that query, right? So there are two parts. On one hand, we need to filter the manifests. And on the other hand, we need to actually execute the data scanning, right? We actually need to scan those files. But Starox, again, because it wants to reduce costs, it does a lot of pruning and a lot of nice optimizations just to be able to read as little as possible and only as much as it's needed in order to return the results, right? Of course, Iceberg doesn't just have data files. There are, well, data also needs to handle delete files, which are still data files, but it needs to consolidate them, right? And Iceberg is quite notorious for how difficult deletes handling, right, are to be able to consolidate them, right? Iceberg has two types of deletes. We have positional deletes and equality deletes, and those need to be handled a little bit differently in order to be able to just return the actual rows that are not deleted, right, and ensure data correctness. With this in mind, we can recap, right? Starox will optimize anything that's related to Iceberg via a lot of pruning, partition pruning, predicate pushdown, column skipping, and of course, metadata caching and data caching on these CN nodes. And at two levels, right? One in memory, but also on disk if you enable. Now, let's see how a query. The idea is, well, the previous slides, the previous diagram was quite lots of boxes. Now we can see exactly what it means. So we have a query that is an Iceberg table that is partitioned by the month of the collection timestamp. This is actually a query that we run, and it has a sort key there, right? Because this is a simple example, right? So we initialize the query, and then we need to parse it, right? And we realize, or the planner realizes actually, that there are that this table is Iceberg, there are some predicates there, and has some applications, right? From there, of course, it needs to look at the catalog and retrieve the main metadata, right? Metadata file pointer, that main metadata.json, where resides the current snapshot ID. From there, right, it will be able to just read the manifest list, right? Because it has the snapshot ID, and you can read them. And at this point, because you know that in those manifest lists you have the partition level summary, you can skip. You can say, okay, well, if my collection timestamp, right, is not the right partition, right, I can just not read any manifest list that would include that timestamp, right, that partition, because, well, I can just filter them out. Finally, we read manifest files, right, and we do more reading based on statistics. So, for example, I'm querying about for this provider. This provider is that big number. If I have a file that only contains providers from 1 to 1 million, I can skip, right, directly. I don't need to read all those files, right? Then I can just distribute the data scan, right? After doing all this parsing of the metadata, I can just get to the point where I say, okay, I need to read only these 3 files. This is all the data that I need, and I read them distributed across multiple nodes, and I can apply any real-time filter at that moment in time, do column pruning, cache that data, and return the result to the user, right? This is the final application, and that's pretty much it. This is the whole life cycle of a query from Starox into Iceberg. Very simple, right? But we can do more than that. We can actually unify a system. So we can say, well, I have my cold data in Iceberg, and I have my hot data in Starox, right? Just because Iceberg is not that great with ingestion streaming yet. Maybe it will in the future, I don't know, hopefully. But we can actually do hot-cold data separation in a sense. So for Starox, where it doesn't matter where the data is from, it doesn't discriminate, it just, each source will get executed in parallel, each query will be executed in parallel with its own execution pipeline. The CBO, the cost-based optimizer, will just apply all the rules that it can in order to improve and maximize the performance, right? We can do something like this. So we have some data in Iceberg, right, with Lakekeeper as a catalog, of course. And then we have other data in our internal OLAP system, and we can unify them without needing anything else, right? It's transparent for the user. Of course, all these models, this is just explanation, but all these models are for us in dbt, and we just select star from one view. That's it, right? How this looks. And this is a plan to ensure we have a visualizer for our Iceberg query, so we can see exactly, essentially, how many bytes are scanned, all the statistics that are used, and we can improve this. So for example, in this case, it took 30 milliseconds to scan in the end. It's not visible in here, but there are like 1 million rows in the specific Parquet file. Right, so this is where I need to hand over to Anton, and we will continue this journey of how we read and how we can optimize these reads and reuse what we have already computed. So, Anton.
Thank you, Nika. So, I'm Anton. How are you? I guess you haven't missed your chance to get some sandwiches. So you are now a little bit sleepy, so I can tell some bullshit, I guess. Okay, so materialized views. So we already talked about caching. So we can cache metadata. What if we cache data? So it's a simple idea, and it's basically what it's about. So materialized views in Starox is about this idea of caching data. So, but there is more to this, because basically, imagine you execute a query and you define a materialized view on some subset of data. And then you reference in your query exactly the same SQL definition. So Starox would actually rewrite this to use materialized view without you knowing. I mean, like you can totally control it with some flags, but it's kind of like a very interesting feature, because if you specify like a freshness guarantees of your query, you literally get it for free. So you say like, okay, I need the most fresh data, so materialized view wouldn't be used. I am okay to get the data 1 hour ago. Okay, materialized view was updated. I can use this data. So pretty neat, but it's kind of like simple. That's how it would look in the next version of Starox. So now we go to the future. And there is a parameter, an option, like a refresh mode, and there are a couple of values here. So the most simplistic one is full. You just kind of like recalculate everything, cache the data, that's it. Then we have PCT. What does it mean? It's partition change tracking. Mouthful name, but it basically means like I need to, I want to refresh my materialized view by partition, per partition. Easy. Then we have like auto. It's decide by yourself. And the most interesting one, which is actually a new addition, is incremental. So incremental is kind of like a neat stuff, but let's first talk about the problems that we are trying to solve with materialized views. So we are talking about materialized view refresh. So imagine that we have like a partition table in Iceberg. So we have sales, partition 1, partition 2, and blah, blah, blah. So, and the only kind of like values that we are updated is partition 2 and partition 4. So do we need to update the partition 1 and partition 2? No, we don't. So that's the whole idea. So we say like, okay, we can actually optimize it and update per partition. But you see these kind of like 10 rows, 5 rows. So imagine that partition 2 and partition 4 is million of rows. And in order to kind of like update and ingest like new 10 rows, we need to update the whole partition. Doesn't feel right for me. Okay. There was the whole idea behind incremental view maintenance that is coming in new Starox. For example, you have still the same 4 partitions and the same 10 rows in partition 2 and 5 rows in partition 4. And we say like, okay, but if you know the exactly kind of like the delta, why we cannot update? It sounds simple. I mean, like the implementation is not that simple. It's all being kind of like supported by a new kind of like type of framework, which is called TVR, time varying relations. So in order to understand what we need to update and basically get the delta, what do we need? We need to remember the last point since we refreshed materialized view. So in this case, it's snapshot 2. Then we have a base table, and it's currently on a snapshot 3. So can we just kind of like compare them and see that, oh, okay, they actually differ only with C parquet file. So we get the delta from snapshot 2 to snapshot 3, and then we say like, okay, that's actually our delta. Now we can do something sensible with this delta. Okay, that sounds simple. What we can do with this? Well, we can do some aggregations. And basically, aggregations work very simple. So we define a materialized view. Then you say like, okay, you know what? Let's define a materialized view and do all the aggregation, all the heavy lifting. And then we have a materialized view in Starox native table. And also we have a states underscore states table. Here it's denoted like a sum underscore state. And it's kind of like a partial aggregate. So it means like when I get the delta, what I can do, I can literally parallelize by key, because remember, Starox is actually MPP engine, so it means that it can heavily parallelize. So I can distribute my load between all these keys and successfully merge these partial aggregates. And in the end, I get an updated NV state. This is the most useful and application of incremental materialized view maintenance, and it works, and it's useful. And now let's get to not so glorious part, joins. So, okay, we get the deltas. And what? This is a kind of like a mouthful formula how to get like joins to work with these incremental deltas. And it's not very nice because, as you have noticed, we basically have a union between kind of like base left table and delta from the R, and symmetric part for the right table as well. So the problem is, in the worst case scenario, you need to process full left table and full right table. And it's actually worse than partition-based pruning, pruning, incremental view materialized view maintenance. Sorry, too many materialized views today. What is the idea? The idea is simple. So let's trace. So we have delta, as I said, like full right part. So we join them, we generate the matches, insert into materialized view, do the same for the rest. The problem is that it's kind of like worse than partition-based materialized view maintenance, but also there are a couple of improvements that we can make. And for example, Starox, in a recent pull request, they actually demoed a join state. So join state is actually kind of like going at the territory, which is familiar for the folks that are familiar with Caldera, Materialize, and other kind of like incremental full materialized view maintenance frameworks. And I mean, like, this is kind of like a simple idea. I think like Starox should go like a long way to fully support like joins working with them. Right now, for example, redirections are not supported, any auto joins are not supported, but at least we can use this framework for aggregations. So key takeaways from this. So Starox is a sophisticated engine for doing lakehouse analytics on top of Apache Iceberg. And it has a lot of different optimizations, from caching metadata to caching data with materialized views. So it abstracts away a lot of complexity connected with operating on top of Iceberg Lakehouse. And there are a lot of various ways with which Starox as an engine can query Iceberg data lake. And because the architecture as an engine, when it has like a separate planner, and you can get a lot of complexity of querying Iceberg inside of engine, which is arguably kind of like a benefit and also like a trade-off. It can support very sophisticated features like incremental view maintenance, which is in early days, but still very interesting to track and see how it goes. So it was wonderful, Nicoletta, with me. My name is Anton. If you like the story about Starox, we have a lot of more battle stories to share. I also kind of like do a lot of streaming stuff, Postgres. So if you like this, you can scan QR code. This is our Fresher Data Engineering blog. Thank you for listening.
Any questions, guys?
I can just yell.
Okay.
Very loud anyway. You talked a lot about the read path, but what about on the write path? Like, how do writes happen in this? And are there any special considerations, like when using Starox in particular, or does it just work? I mean, the promise is it just works.
Starox actually added like a write support in Starox 4. So right now you can actually write an Iceberg from Starox, and also it supports that ordering and other kind of like optimizations. But also any other external engine can be used, and then you just need to register your metadata in the catalog like Polaris or Keeper, and that's it.
There are some easy constraints to write into Iceberg, like dealing with snapshots, data for compaction. And personally, I think that it's not the purpose of the query engine to do that. The query engine is really to request the data. The 5-strand, OLEG, whatever, absolve they do the ingestion, and they are good for that. So I think that
this part
in the ecosystem, there are different approaches.
Yeah, I mean, like theoretically, is the right part when you can tier your data from Starox native to Iceberg. It's kind of like good, but maintenance as compaction, it should be offloaded to some other more efficient tools.
I mean, that's my question also, if I may. How do you deal with the small file issue we have in Iceberg?
Well, we have Spark workers running this, but basically we use our Iceberg in a very conservative way. So we say like, okay, we have a set of cold data, which is basically mostly immutable. And we have a hot data, which is handled by Starox. And we have like a cutover point where we can say like, okay, this data in Iceberg is mostly immutable. So we can work like this. Also, you can tell, okay, but what about if we have sometimes rare updates, deletes, and whatever like. So we accumulate this stuff in some staging tables, and we have still use union read, and we need to deduplicate and other stuff, and it becomes slower, and it's a lot of trade-offs, of course, with this. So we try to use Iceberg as mostly immutable storage, and it works. But when we have to deal with this, sometimes we actually say, like, you know what? It's very complicated. Let's just use Starox native. I wouldn't deny that we do this.
Do you have benchmarks compared to other distributed query engines?
Benchmarks. I mean, like, we benchmarked when we evaluated like Starox, and I think like yeah, we benchmark kind of like with just Spark. Then I think like with DuckDB. I mean, like, I liked that Starox is kind of like a combine that actually allows me to kind of like configure all these caching from metadata to data files. So, and also it kind of like provides a lot of scene nodes. So it's a little bit hard to kind of like measure like benchmarks when you say like, okay, I have, for example, Trina and Starox. They work a little bit different. So at least everybody knows like the problems with Trina cache. So in this sense, I mean, like, yes, Trina was slower in this sense, like 3 times in my own benchmarks, which are not very accurate, to be honest. But I was just evaluating which engine we want to choose, not only for Iceberg, but also for real-time analytics. So the question was first, okay, what do we need to use, like ClickHouse or Starox? And then the second question was, can we support Iceberg as well if we need to kind of like tier the data and query call data? So it was benchmarks mostly about like with ClickHouse, and the second set of benchmark was about like how comfortable is to use Iceberg.
Cool. Well, thank you again, guys.
Okay.
Thank you.
Now it's your turn. Now it's your turn. Yep.
All right. Can I just get? Thanks. All right. So. So I guess I'm online here. All right. So I will probably skip all slides. I won't actually talk about very boring topic, business continuity management. You know, like when you insert your data, your table is broken, your boss is yelling at you, and you need to do something on that. So what you do, you will probably call your ops guy. Do we have a backup? Can we restore the table? What should we actually do in that situation? And that's like the daily business of everyone who deals with Postgres, Oracle, SQL Server. So because if you do an insert, it's all on your table. But we have Iceberg, and Iceberg has some quite cool features because the structure of Iceberg basically snapshots, and Iceberg has built some functionality which you pretty much aware of from developing your code. It's branching and tagging mechanism. And that's something what I want to actually demo today. And I hope I can do that. Yeah, there are some screens as you can see. So let me just go to. So what I'm gonna use is well, some code. Let me just increase it a little. So no, that's the business continuity management has probably nothing to do with business, but that's something what we have here. So right now, what I will do is actually I will connect to. In my case, I run the Iceberg catalog on-prem, and I use Lakekeep as a catalog, and then I use Spark, and I want to just write some data here. So what we will do is just initiate the client itself. I guess it does work. And then let's just create here the first table where you can see that we have a table named salary, and we have Alice and Bob. And actually what I want to do right now, we'll go to, in that case, to Lakekeeper. And here I have all my warehouses, and we used the Amazon Web Services here, demo STS. And then I have a namespace brunch and tables, and I have a salary. So what I want to do right now, I go to the preview, and I want to see actually my data, what I was inserting right now in Spark, and you see the same data here, right? So Alice and Bob, and you see same salary. And the cool part right now, I can see the table. So I will go to the versioning, and I see exactly this single snapshot here. And I can actually click on that snapshot, and I can get a lot of details about that snapshot, what is happening here, so the schema, the stuff, and so on and so forth. So let's just go back to our data processing time part and just add 2 additional employees, Max and David. Well, I guess both from SF. It's why it's so high revenue here, so high salary. And if we go back to a preview of that table, we will get exactly that data right now that we just added here, right? The cool part is because it's all snapshot based, we can actually use the time travel. And you see that I actually did 3 operations of that. So I created 3 different snapshots, and we can actually go to the first snapshot and see how the table was initially. And I can go back to the second snapshot and to the fourth snapshot. Now, the next thing is, because now I will want to just do some changes with my table, but before that, I will create a tag. And if I go now to my versioning, I will see exactly 3 snapshots and a tag. And you see we created a tag recovery point. And that's the last snapshot, and we have our recovery point. And the next step, what I want to do is actually, I want to create a branch. And now I want to load in that branch. So if I will here refresh, I will see now that we have the audit branch here created. And what I will do right now, I will actually load inside the table inside of a branch. So which means if I run it here, it will take a while here, and we will add data. So let's just refresh. You see exactly what is happening here. So we have now 2 additional inserts and updates, and we will see exactly what happened at that snapshot. So we will just go back to the preview. So the let's say someone with Starrocks or with other tool will run on a main branch, select star from table, and will still see the initial state of a table because we didn't expose, we didn't merge that branch yet. But if I will go to the audit branch and to the last snapshot, I will get actually way more data at different states. So we actually updated Bob. So Bob has now more money, and Anne has more money. So we did some changes here on that table. And going to versioning, you can actually even compare snapshots and say like, okay, so how was it like before change and the after change? And you see all that information about your Iceberg table, what happened here. But now getting to the fun part. So let's imagine we did that on Friday, right? And Monday, our boss just get back to and said like, okay, so what did you do? I did some updates. Okay, make the table ready. So what you will do, you will just go and say, fast forward to the main branch. Now, when someone will run selects down on that table on the main branch, that data is now available. So so I just fast forwarded with the whole stuff here. But suddenly our boss will tell us, well, we did a mistake. We don't have that employees yet, or salary was not kind of given to that employee, whatever. But what we actually did before that, we already, let's delete the audit branch because we assumed we don't need that anymore. We now have a situation that we kind of deleted and changed the data. So how to restore the whole stuff? Well, the part is what I will do before restoring the stuff here, I will create a tag on this one just in case. And what I want to do in this case as well, maybe just to show you that if we completely clean the whole stuff, so right now, that would be like our state that we don't have like the data anymore. But what we can do, we can just go and say rollback to the previous on Friday state. No, roll back. And if we go back to the table, we will get again the state before any changes. So that's your backup. That's how you can actually make a very, very simple way of business continuity management in case you did any changes. But imagine like the situation 1 hour later, someone will get to you say, no, everything was actually proper and as expected. And you were just, like, okay, we have actually the tag on that just in case. And now what we want to do actually, because the stuff was actually exactly as expected, roll back to snapshot 5. And if I will go again to the table, so all the job, what we did, let's say on weekend, is still there. So it's not gone. And nothing with your classical way, as you probably know from your Postgres, where you will go and try to get the backup and somehow drop the table, roll back, and do very, very long processing. Through Iceberg and snapshot mechanism, it's super easy to achieve that. So you can imagine that from a different perspective, what you can do with this type of mechanism in terms of business continuity management, when you want to just have a simple backup restore mechanism. Or maybe you're a data scientist and you want to actually say, I want to train my AI or ML or whatever you do, but on a stale data. Data should not be changed in that process. A more funny example is like when I talk to financial services, they're saying like, oh, my regulator is trying to get back to me 5 years later and asking like, oh, you run this calculation, we need to reproduce it. And you can imagine like on a classical database table, how hard it can actually be to make any reproducibility. In case of branching and tagging, it's super easy because what you need to do, you need to tag or create a branch, tag it, run the calculation on that. You have your code in Git, you have data, Git-like. It's not a Git, but it's kind of like quite similar. And if you need to reproduce, if you need to create your business continuity management, that's something what you can achieve easily with Iceberg, which was not possible before Iceberg. So that was my idea, just to show you some kind of boring stuff, but that's how Iceberg is actually working under the hood. So you have snapshots, you have branch and tags, and you can actually achieve a very interesting use cases as like with database not even possible today, I would say. Yeah, so I would probably stop here. Any questions to snapshots, branch and tagging? Go ahead.
Can you do schema evolution on your branches?
No. Well, you can only do a schema evolution in the main branch.
Actually, the reason is schema is part of the metadata.
Yeah.
It's not part of the data. So if you add a new column, it's going to be for all snapshots basically.
Yeah.
And it's normalized by Iceberg design, I would say.
Yeah.
But
I know that from feature or
It's surprising, but yeah.
But yeah, absolutely, it's quite interesting. If you want to load new data, you will create that audit branch. You will change the schema, load the data, and say, "Oh, looks good. Let's do kind of like fast forward." Not possible.
And by the way, that's why we have the default values. So default values, you have an insert or an update. So you add new values for a column, and that's basically you decide if you do initially or when you add a new column. And the way it works, I mean, I did that, so I know but that could be tricky depending on the schema and the type of the. But it's with variant, it's pretty hard to have default values. So yeah.
All right, we have 2 more questions. Yeah, go ahead. Yes, go ahead.
So if this branching and tagging was native to Iceberg, or
Yes.
have a specific
No. Iceberg and tagging is native to Iceberg on table level.
Branching is also available everywhere.
Say it again.
So you showed branching concept and also tagging concept.
Yes.
Right? So is both branching and tagging native to Iceberg and available on all catalogs?
Well, the first part is it is native to Iceberg, and it's up to catalog implementation to enable. But yes, it's more like on a engine side that engine supports to create a branch, to create a tag. But it's just a spec in Iceberg catalog, REST catalog, probably REST catalog, right? So yeah.
So to answer your question, yeah, both at demo level are part of Iceberg. What is not part of Iceberg, it's catalog level version, where you can have one branch for multiple tables. That is not supported by Iceberg. That's up to the catalog to decide if you want to support it or not.
So if you want to branch and tag a table, that is native Iceberg feature.
Just a question in terms of strategy for snapshots. Like I can see an example, like you ran a particular query. It may not be obvious at that time that that's going to be audited in 5 years. So what kind of scenarios and strategies have you come across in terms of when to make those snapshots? Like I could picture maybe like a daily snapshot becoming a habit, but like, yeah, what's your experience in terms of when to sensibly checkpoint to avoid the disappointment of, well, I never committed that thing, so I can now never see it again.
Yeah, to answer your question, you need to understand who you want to disappoint inside of your company. Like you want to disappoint your CEO because your costs, like exploding because you have so many tag and snapshots, or you want to disappoint your chief revenue or risk officer because now you cannot actually restore the table or reproduce the table. So that's kind of like to answer your question. So it's in inside of your company, and it's, I guess, even not for the entire company, it's per use case where you can define that strategy. So you can say like, okay, I have, I don't know, like a very kind of not important use cases where 30 days of snapshotting is okay, and then we can just expire snapshots. But then you have like a kind of a financial services use case inside of your company, then you will probably rethink that strategy and think in a different way and say like, okay, we will keep all that snapshots. We are ready to pay for a cheap S3 storage. Unfortunately, there is no archive snapshots. Like it would be nice just to say like, oh, let's just put all that snapshots to Glacier and then not paying that much. But that's, I would say, a missing function, and JB is going to make some motivation for the open source, and probably that's a cool feature request. Yeah. Go ahead.
What are the scaling bottlenecks with this in terms of, I mean, obviously, right, if you've run Apche for a long time, it's in the storage, but yeah, there's also affected queries, right? Because manifest this, manifest files, etc. All these snapshots need to be kept around. Where is it going to creak in?
Yeah, well, yeah, absolutely. I recently in Iceberg Slack, I saw the message that someone has metadata of 20 terabytes. So that will have an effect on your query in a way, right? So, and therefore here as well. So if you have all that snapshots, especially like if you want to run expire snapshot, your query engine needs to understand, or like the optimization vacuuming engine needs to understand, that snapshot should not be touched because you have a tag on that. So it will take longer, and then therefore it will make my not that easy decision. But again, if it's 20 terabyte metadata, well, it's probably kind of too much. But I would say in a usual use case, you're not going to hit that many issues, I hope. But please let me know if you have a different experience. Yes.
That's where you need table maintenance. You need table maintenance for snapshot eviction. You need table maintenance for data file compaction. And that's basically the catalog that can provide the policies to trigger the execution of table maintenance by your query engine.
But you'll be impacted for more kind of maintenance.
Something you cannot
find out too late.
That was my question, but small file issue because in V3 of Iceberg, that's pretty classic use case.
Yeah, so if you have your tags on the small files, they're not going to be compacted. They're going to be there. It will cost you something.
And it's where a catalog like Lakekeeper also helping, because if you have access directly to metadata.json, it could be huge because you have all the snapshots, all the partitions, everything. With Lakekeeper, you can filter, hey, I want just the latest snapshot on this table. So you can optimize already the reading of metadata.json.
So you imagine, like, I have a small table, but that's kind of like a snapshot. And then all that IDs will go down there. And then you have somewhere ref with all that different tags and branches. And, you know, like that's something can be very big. And then you have all that manifest lists and manifest files. I know like V4 might be in a, everything is going to be better. That's kind of like the main promise. But that's something what you need to think about. All right. Cool, guys, thank you very much. Now we have like 20 minutes break, no sandwiches, but I guess some drinks. And in 20 minutes, we have 2 more talks, so don't run away. See you soon.
But I'm gonna have a. Can work. Yeah.
All right. So that's going to be a lightning talk. And the purpose of this kind of meetup is also to have interaction. So feel free to ask any question. I'm going to ask you some questions, by the way. So we're going to have some goodies for you if you are able to answer. So I'm JB. I'm director of the Apache Software Foundation. And I'm PMC member on more than 20 Apache projects. So who knows what PMC means? Who wants to try? Zander?
You guys run the project as a whole, maintain it.
And PMC, what does it mean? The three letters.
Oh, you want the, oh, hell.
Aha.
Committee.
Committee is the C, yeah?
That's 1/3.
Project Management Committee. You got it. So PMC is basically, so it's not a technical people in a project, it's more governing people. So that's basically the responsibility of a PMC is first to elect new committers, elect new PMC members, and they vote on the release. And sometimes when you see a release on Iceberg, for instance, you can see +1 binding or non-binding. The binding are the vote from the PMC members, okay? That's the most important people in a project. And on some project, I mean, on all projects, sorry, there are one PMC member who is promoting as a PMC chair. So the PMC chair is not a leadership position, it's just an administrative position. And the purpose of a chair is to report to the Apache board every quarter. So every quarter, we receive a report from all projects, I mean, saying what's happening in the project. So for instance, I'm PMC chair for 3 Apache projects. In the Iceberg ecosystem, Polaris, maybe you heard about Polaris. I'm the PMC chair for Polaris. I'm not the leader of Polaris, not at all. I'm just doing the administrative part. So that's for the PMC chair. And the first question is, who knows what is the ASF? Apache Software Foundation, yeah. What does it mean? What's the role of the ASF? Do you know the difference between the project and the foundation? Because since the beginning of this meetup, I heard about Iceberg, Iceberg, Iceberg. That's completely wrong. It's Apache Iceberg. It's Apache Iceberg. And the question that I have for you, for these goodies is, what's the difference between an Apache Software Foundation project and an Apache license project? StarOx is under the Apache license. What's the difference between, or Lakekeeper is an Apache license. What's the difference between an ASF project and Apache license project? Yeah, go ahead.
Are they funded by the ASF?
No, there are no money at the ASF, unfortunately for me. If someone say to you, I'm employee of the ASF, he's a liar. We are all volunteer. We are 5 people paid by the foundation. That's the infra to run our infrastructure. Exactly, you got it. So the governance is super important. An ISF project, well, it means 2 things. First, it means that the license won't change. It's going to stay Apache license forever. And we have recent example about open source project that change the license. And you as users of this project, you are just struggling. Elasticsearch, HashiCorp, Redis, okay? They are all mini IO recently in the different, okay? They all say, yeah, we are open source. No, that's not true. You are open source, but governed by a single vendor. And that's an issue for me, because you as a user, you don't know what's going to be the next step in this project. Apache Iceberg is not driven by Databricks or Snowflake or whatever. It's driven by the community. And so not a single person decide about the future of Iceberg or when to add new committers or when to do new release. It's community driven. And that's super important because today in this ecosystem, we have a lot of change where people want to do money with open source. I have nothing against that. I mean, that's cool as soon as you know how to do that. Maybe you can have a foundation as part of the Apache Software Foundation, and you build your product on top of that. That's probably a better approach. Okay, so that's the difference between Apache licensed project and ISF project. And so do you know how many projects do we have at Apache right now? In the foundation? 200. You said 200? 1,000? Oh, I would love to, but no. No guessing? You said?
500.
Yeah, you're close. 350. Okay, so a project can start directly as a top-level project, a TLP, or can start as an incubator. So probably start in the incubator and then become a TLP. Or if you have only Apache people, you can become TLP directly. That's also an option. So each project are completely autonomous. They decide about everything in the project as soon as it's compliant with the Apache Software Foundation guidance and policies. And so the people who decide about these policies, that's the Apache members. So I'm going to give you some numbers. Let's guess first. How many committers do we have on all Apache projects? We have 350 Apache projects. How many committers? Just guessing.
5,000.
More than that. Yeah, we have between 7,000 and 8,000. It changes every day. Okay. How many PMC members? A little more than that. We are around 3,000 PMC members. Okay, so we have 8,000 committers, 3,000 PMC members, and across all these guys, there are some Apache members. So the Apache members are people that work on different Apache projects, and they are not involved on a single project. They can become member of the foundation. Okay, that's the Apache members. Do you know how many Apache members do you have? Yeah, less than 1,000. We have 900 people, Apache member. And across all these Apache members, we have 9 guys. They have a board of a foundation. I'm one of the 9. I'm the only one. I was the first French guy. So today in the 9 people, we have different profile. And we have 9 directors to manage, to decide on the budget, to decide about the policies, to also appoint the president of the ISF. So basically, it works exactly like in a company. We have a president. If we are not happy about what the president is doing, we just fire the president and we put a new one. That's exactly like in a company. Okay, so that's the ISF. That's basically what it matters. The most important is vendor neutral governance. So sometimes I see that Kafka is Confluent project. It's killing me. It's Apache Kafka. Okay, so that's super important. Apache Way. Maybe you heard about Apache Way. Do you know Apache Way? Yeah, go ahead. Community of the code. So what matters in a project at Apache is not the code by itself. Okay, it's important, but it's the community, because if you have a community, long term, your project is sustainable. because the code at some point can change. And with the AI today, the code is very disgusting. Okay? So meritocracy also. You are rewarded based on what you do. Okay, more you do on a project, more you can speak. Okay, I'm PMC member just because I'm a PMC member, because I do things on the project. I try to help the project. And the contribution is not only code. Any contribution is very valuable in a project. Documentation, website, helping users, activity on the main list, license check. In Iceberg, for instance, we have one guy that has been promoted as a committer and now he's a PMC member, mostly because he did a lot of help on the communication website documentation. Okay, the same in Polaris. We have one committer. She's involved a lot in the communication website, and she never did a single line of code, but she's a committer on the project. So any contribution is very valuable. Iceberg. Who can say to me, I'm gonna go to the next slide because you have the answer. What is Apache Iceberg for you? How do you describe Apache Iceberg? So you're gonna say it's a table format. Okay, fair. But from an Apache project, what is Apache Iceberg? Correct, you got it. It's 4 specs. Table, view, Puffin. Starhawk, are you using Puffin for statistics? Okay, REST catalog spec, 4 specs. Now you have 2 options. Option 1 is you implement the spec by yourself. You just read the spec and you implement it. Google did that. They don't do that anymore, but they did that in the past. They started from the spec and they re-implemented everything by themselves. Or you can use some libraries provided by Iceberg. Java, Rust, Python, whatever. Okay? So in a nutshell, Iceberg is just a set of spec. I don't want to go again in terms of where it's coming from. It's coming from Hive, actually. Okay, the reason why Iceberg has been created is because at Netflix, the guys, they struggle with Hive. And so they wanted to find something fixing all the issues they got on Hive, and they created basically Iceberg. So you know that already. I mean, Victor showed us about snapshot, time travel, schema evolution. We discussed about that, as transaction, partition evolution, all this stuff. You know that. If you don't know that, just ask. We can discuss about that. And that's basically the ecosystem. So the data layer is where you have the data files, Parquet, Orc, Vortex. Okay, it's where now in Iceberg you have the data file API. That's something new that has been added. I mean, we started, what, 3 months ago, something like that. And so now it means that you can replace the Parquet files by something else of your choice. I'm working on the Arrow implementation for this data layer. On top of that, you have a metadata layer, metadata.json, everything that Victor showed us. The manifest list, manifest file. That's v3 on Iceberg. v4, you forget about manifest list. It does not exist anymore in v4. Okay? So v3, that's the way it works. You have a new kind of type like variant, geospatial type. You have default values. You have multi-arcs transforms, stuff like that. Do you know multi-arcs transform? No? So when you create a partition, you can create a partition based on a column. You say, I'm going to take a partition every month, for instance, and to calculate the month, you're going to use 1 column. It's what we name a transform. In v3, you can use a single column. I mean, before v3. And now in v3, you can have multiple columns. So you can compute the date based on 3 columns, for instance, but multi-args transforms. On top of that, you have a catalog. So the first purpose of a catalog is to track the metadata, nothing major. That's the way it works. And that's basically the ecosystem. It's not exhaustive, right? You can see new stuff. So basically, I tried to identify 3 main categories: query engines, Spark, Flink, Impala, Dremio, Trino, Starworks, whatever. Catalogs, Polaris, Gravitino, Legkeeper, HMS, Nessie in the past, stuff like that. And tuning and integration is more global. It's basically where you can find Fivetran, Amoro. Do you know Amoro? No? Okay, Amoro, NiFi, Camel, Kafka, Parquet, Arrow. I can add Fuzz. Do you know Fuzz? Okay. So I'm one of the mentors on the Fuzz project as well. So that's the kind of ecosystem. So that's mostly based on Apache stuff, but you can imagine we are OLake. I should have put that. Sorry, I forgot. So why does it matter? Is because it's a real world adoption. I mean, it's really used in production. Okay, I'm working for Dremio, so I can share a lot of details about. Mike is there, so he can share also a lot of production use cases of Dremio and Iceberg. I try to identify different people using Iceberg. You have Netflix that are still using Iceberg like crazy. They are not only using Iceberg, but they are huge users of Netflix. Apple, LinkedIn, Adobe, they are using large-scale analytics, also based on Iceberg. The cloud service provider, so Dremio Cloud, for instance, is one, but you also have AWS with S3 tables. Maybe you saw that, S3 tables. Azure, GCP, stuff like that. You have this usual suspects, so Snowflakes and Databricks in the pure Lakehouse market. Fivetran and Datadog, because we do mostly integration and collection. Datadog is fully based on Iceberg now. Okay, it's a huge change we did recently. 2 years ago. But they are using Polaris also. That's a huge integration. And this is a growing community because there are a lot of use cases we don't know, basically. So why ISF governance matters is exactly what I said. And I think it's one of the reasons why Iceberg has been so popular and in terms of adoption. If you compare Delta and Iceberg, for instance, to the table format, that's a different kind of adoption mechanism. Do you know other table format at Apache? Simon? You already have one. Hoodie? Hoodie is number one. So you can see that at Apache, we have different projects doing exactly the same thing, mostly using maybe the same technologies. Kafka, Pulsar, Gravitino, Polaris, Flink, Beam, Spark. That's pretty blurry. Do you know Beam, by the way? Apache Beam? Okay. I mean, there are a lot of examples, and typically Payment, Hoodie, Iceberg, same kind of ecosystem. Do you know a project that can convert from one table format to another? At Apache? No? Apache Xtable. Xtable is a project that can convert the metadata from one format to another. Okay, I'm not sure it's a good idea. I just share the names, okay? But that's really interesting. They propose something to integrate Xtable as part of Polaris, for instance, to be able to support Delta and convert into Iceberg tables. Again, I'm not sure it's a good idea, but anyway. Yeah, go ahead. Yes, but not UD or not Delta. That's right. Okay, so why the ISF governance matters? Adoption, community-driven. The fact that Iceberg completely decoupled the spec from the implementation, that's also something we like at Apache. Do you know other projects at Apache working like this? I have one spec and I have multiple implementations. I said the name already. No, yes, kind of. You have the half of the. I think yeah. You're gonna take it after. I'm gonna shoot someone there. Arrow is exactly this. Vector is the specification, and you have implementation in Java, in Rust, in Python, etc. So Arrow is another one. And that's it. Any questions or comments or whatever? It was a lightning talk, so pretty quick. No questions? Yeah.
You mentioned that some project was donated. How does it work? Because basically you have a project, so you develop as a company, then you donate it. How are the PMC members, committers, and other stuff, how it works? Do they actually go Apache ways, so not to get like governed by this organization that donate?
That's a great question. If you want to donate Starworks at Apache, why not? And by the way, is it recorded? Okay, so I can share some names, not recorded, but we have a lot of discussions with existing projects that want to join the ISF. How it works is basically you create a proposal that describes a project, and it goes into the incubator. You are not directly a top-level project, you go through the Apache incubator. So in this proposal, you're gonna have mentors, so people that are gonna help you to shape the project, to define the governance, and then you define your PPMC member. Why have I said P 2 times? PPMC members. Podling. Podling means project into incubator. So PPMC means Podling Project Management Committee. And so you start like that. You sign your SGA, Software Grant Agreement. So basically you donate your IP and your trademarks to the ASF, and you are good to go. You are starting as a new incubator project. And during this incubation period, after usually a year, you can become a TLP. So the first thing is you need to find a mentor. If you don't have any mentor, you need to find a champion, someone gonna help you find mentors so true story, Polaris. Polaris started at Snowflake. Before being an Apache project, it started at Snowflake. Snowflake called us, Dremio, and called me specifically, hey, we want to go at Apache. And we want to collaborate with Dremio, and we want to co-author Polaris. And so it's the way it started. We started to contribute on Polaris before being an Apache project. And then I drafted the proposal. I find resources, I found people, and then it becomes Apache project. That's the way it works.
But still you need to find a mentor.
Yes. Yes.
Call JP.
Yeah, you can call me if you want. Beam, the same. Beam, it was the data flow SDK. It was a project from Google. I was the mentor on Beam as well. Another question, yeah.
There are obviously a lot of projects with Apache, but how do like PMC members from some ecosystem talk to and organize with other PMCs? So specifically, I'm thinking in the sort of data fusion commons world, their work and direction is obviously directly correlated with the Iceberg world.
So,
like, is there a sort of group coordination?
No, but not formally defined.
Yeah.
It's informally defined. Data fusion is a good example because it started as a sub-project into Arrow. And then it evolved to a TLP. So in data fusion, we have people involved in Iceberg and others. So that's informally, I mean, that's what I'm doing. I'm in Iceberg, in Polaris, in Arrow, in ActiveMQ, in Kafka. And so I can connect people and try to have some kind of consolidation, but that's a huge difference if you compare the Linux Foundation and the Apache Foundation. That's a huge difference in terms of model. So disclaimer, I have nothing against the Linux Foundation, but Linux Foundation is an amazing marketing machine. Amazing marketing machine. But they are not enforcing anything about governance. It's a pay-to-play model. So you pay, you're gonna govern the project, which is not what we do at Apache. Eclipse Foundation is closer to Apache Foundation. So it means that in one project, you don't have sub-projects. I mean, but something also that I explain a lot, you are committed on Iceberg because you contribute on Python, or Rust in your case, you are committed on the whole project, not only on Rust or Python. They are a single governance. That's a huge difference compared to Linux Foundation, where you can create sub-projects. I mean, CNCF is just a sub-foundation of the Linux Foundation. And so inside a project, you can have sub-projects. It's not something we do at Apache. Yeah, well.
So you said there's lots of projects, and you consider multiple projects. And you also mentioned there's multiple table formats, multiple Apache table formats. Is there such a thing as a conflict of interest for a board member?
No, so that's a very good question. There are no technical requirements to accept a new project at Apache. What matters for us is, do you have a community around your project? If you have a community with your project, it's good enough to be an Apache project. I'm going to take another example, the last one, because we are running late. Maybe some of you know Apache ActiveMQ. No? It's a GMS broker. In ActiveMQ, we had two projects, not a project, but two code base, two repo, Artemis and ActiveMQ. And both, I mean, I'm working on both. But we decided, because we have two communities, the Artemis community and the ActiveMQ community, we decided to split, because there are two different communities. The same for data fusion. The reason why data fusion become a TLP is because you have community only on data fusion. We don't care about Arrow, basically. So but it's good enough to be a TLP. So it could be surprising at first glance, because you have the feeling that, hey, there are no technical direction, but community over code. Technical direction doesn't really matter. What matters is really the community behind the project.
Cool. Well,
I'm done. Thank you.
we have our last speaker.
I think should be good enough. No, on which? Yep. Here it is. Yeah.
Now we can just go.
Yep. Hey. Hello. Hello. Yep. I think we are good to go. Hey, I'm Shubham. I'm one of the co-founders and a CTO at a product called Olake. So I'm going to present to you a topic called reimagining Iceberg ingestion and table maintenance. Quick introduction about me. I have been a data geek for the last 10 years. I've worked with multiple companies in India and Japan. This is my first time in London. I landed on Saturday. I wanted to see London, so I went on a walking tour on Sunday. It was the worst decision. I didn't know about the weather here. I come from like 35 degrees Celsius. Yeah, so quickly starting, I don't have a lot of time, and I'm pretty sure you want to go home. We have talked to almost 200 odd companies 18 months back, who were thinking about Iceberg, who wanted to adopt to Iceberg. And one of the first problems that we saw was a lot of these companies, like especially around the enterprises, early enterprises, they have like huge scale, and people who are thinking about adopting Iceberg, they have like a good scale. And usually either they were thinking of creating the pipelines themselves, or they were thinking of using a managed ELT solution. But I think one of the problems with that, the existing ELT or managed solutions, they were like really good for like a couple of GBs to a couple of terabytes. But I think the scale that they were operating on was like a couple of 100 terabytes a month. So that's where we decided, I think there are a lot of people who need help with this. And also, like, the existing managed ETL solutions or any other solutions, they're really good or focused on warehouses, but Iceberg is like more recent development. So like they basically, it's just a spec, as people mentioned before. So for spec, you need to ingest the data, and also you need to maintain the data yourself. For warehouses, it's more like a fire and forget kind of a thing. You insert the data, warehouse takes care of almost everything. So, and also the existing ETL solutions in the market, open source or the managed ones, they are kind of they're more generic in a way. Like, they take data from M sources and get into end destinations. And one of the problems that a lot of people were facing in getting the data from like a high volume sources like databases, Kafka, S3 into Iceberg, at least almost like 50% of the people said that they were kind of facing problems with the 200 people we talked to. Then the second problem was that the complex kind of a tech stack. Almost 20 to 25% of the people we talked to, they said like the Iceberg ecosystem is still evolving, and they don't have a lot of knowledge about Iceberg or the number of tools that they have to use. So like a couple of tools that you need for like data ingestion, you need 2 or 3 tools. Data observability and data optimization, you need like a couple of more. Then catalog governance, you need a couple of more. So and a lot of companies who are maintaining it in like self-managed way, they usually start with Debezium, Kafka, and then Spark Streaming or Flink, and then get the data into Iceberg. And this is like pretty heavy stuff. I used to work at PayPay. It's the biggest fintech company in Japan, and we had like team of 3 data engineers just to maintain this pipeline out of 10 data engineers. It was pretty difficult back then. We were using Apache Hudi, and also like once you ingest the data, it needs like, because you're ingesting at a lower frequency. If you want to go anything below like an hour, it's also something that a lot of companies, they faced a lot of problems with. They were not able to, like, half of the people we talked to, they were doing like, who adopted Iceberg, they were doing like T-1 frequency compaction, like almost 24 hours compaction kind of a thing. And that was also pretty expensive for them. And apart from that, like, this is something like a business side of the problems. A lot of companies who have already invested in the data pipelines over the years, they have put in like a good amount of money to create the data pipelines the way they are today. Like their data warehouses, I don't know, data lakes, or any of the popular solutions out there. They have like 6 to 7 layers of medallion architecture. And if they want to think about moving to Iceberg, it's pretty like a big change org-wide, because, as Victor mentioned, you don't want your boss to like scold you in the middle of the night, like, okay, you have done something bad and now I'm not able to see the dashboards. So this is like, I mean, they want to move to Iceberg. They like the benefits that Iceberg offers, but it's like kind of it's just a big decision for them, because they have already spent so much, and it's already powering a lot of dashboards, a lot of analytics in the organization. I'll come to this problem a little later, why a lot of people are a little bit scared to do this. So we thought, like, why not we solve all of these problems? And that's where we decided to think about like what kind of optimizations and techniques that we can do in order to make this process more better. So first optimization that we thought of was like a lot of these databases, especially databases, they have huge amount of tables, like big tables in terabytes, and people want to sync those tables into Iceberg. Ideally, Iceberg is like you don't have a lot of write throughput, which is restricted in Iceberg. You can actually write as much as you want, because it's end of the day, it's just dumping the data into S3 and then registering it into a catalog. So we decided, like, for the big tables, which people usually face a lot of problems with, we can divide those tables into multiple smaller chunks, and then take those chunks and parallelly stream the data into Iceberg equivalent, like a Parquet, and then register those Parquets into Iceberg, right? Like we have different strategies for databases. Like for Postgres, we have CTID based division of long tables. For MongoDB, we have split vector, and also we have added a couple of new strategies for Oracle and MySQL recently. Apart from that, like one of the thing that people struggled who wrote their own scripts to get the data into Iceberg was exactly once delivery. So exactly once, like basically if you write your data into Iceberg and when you write that data, if you're writing it back into some state file, like, okay, this is the flag that, or this is the point that I have written the CDC into my table now, and this write to the state fails, you would end up duplicating the data when you start processing it again. So we kind of use Iceberg snapshot metadata to store, like, okay, till what point we have exactly done, and when processing it the next time, we'll check from the metadata that if we have already processed this or not. So kind of we have implemented exactly once using the Iceberg snapshot metadata itself. Obviously, we have worked a lot around, thought a lot about like how can optimally create the file sizes of around 500 MB when we do the historical snapshot of the data. And watermarking and resumable full load is something that also a lot of people struggle with. So watermarking is something like if you're doing like 100 tables CDC every day, and you want to add like one really, really big table, like 101 table, which is like a huge. So you would have to pause your CDC and then do the historical load of the data and then kind of continue the CDC again, right? Because CDC is like a one linear, like basically wall logs or bin logs are like one linear logs in like an order. But the Iceberg, we can actually make it better. We can dump all of these, the new table CDC data, we can keep on dumping into a temporary table, and then we can take we can continue flowing the other parts of CDC into the existing tables, and we do the full load while this is happening. And once the full load is done, we can actually dump this temporary CDC table into the Iceberg, the new table itself. So that's how we can implement like a better watermarking compared to what Debezium offers. And then obviously full load, because we chunk, we know how many chunks are done, so we can actually do a resumable full load. And also we are also doing some level of I will not call it innovation, but more optimizations. Like as I mentioned, we are for the sources where we can write more parallelly. We are writing that and then registering it sequentially to avoid the conflicts. So especially for Kafka, we can configure the parallelism on parallel writes. So this is also a learning, like while we were thinking of how we can design a Kafka as a source. For a lot of databases where the CDC happens, it's a sequential read for especially like relational databases, but we can write it parallelly. And we are also we soon realized that we have to do something about the table optimization. So we took an inspiration from a project which JB mentioned called Amoro. So we took that, we forked Amoro, and now we are basically creating like a more OLake or like a ingestion specific transformation. Like mostly like a small first thing would be like you convert your equality deletes to positional deletes. The second thing would be like you convert those small files into like a medium level files, and then the third would be like a medium level to the target file size that you have. So this is something that we are also we feel that people will have to do because they're ingesting data at a much lower frequency. Some of the people who are using OLake, they're actually going as low as 30 seconds in ingestion. So we thought like they will definitely need a much lighter version of compaction compared to the ones that is there, because you're creating a lot of smaller files with the time. And I think, we are definitely using Arrow. Arrow has been like a really lifesaver for us. I'll come to the Arrow part a little later. So this is just an introduction talk about OLake. So OLake is an open source Apache 2 licensed project, and it's like we'd like to call it like the fastest way to replicate and optimize your data into Iceberg. We are fully focused on Iceberg. We love the open nature of Iceberg. That's why we have open source ourselves. We have written it from the scratch in Golang. We have all the major databases and high volume sources like Kafka and S3 supported today. We are also going to add data warehouses as a sources in the next versions to come. It's a pretty simple UI and orchestration in a Docker Compose. You can also deploy Helm charts in production if you want to use it for production. We also have a Helm chart open source. And obviously, as I mentioned, we are going to launch an optimization feature next week as a part of OLake. Just a quick high-level overview, OLake, all of the databases you sync using OLake into Apache Iceberg. And then you have an optimization kind of a module, which is it's not tightly coupled with the ingestion layer, but you can also optimize the other tables that you want to have, like you have in your Iceberg Lakehouse. You can kind of ingest and then compact, and then you can query using any other query engines that you have. So just a quick sneak peek about the compaction feature we are launching next week. So you can configure like all the tables. You can see all the tables. You can add new catalogs. You can see the health score of the tables, and also you can decide like at what frequency you would want to compact, like light, medium, and full. And also you can basically enable this compaction going forward. So this compaction feature is right now, it's definitely a lot closer to Moro, but we plan to take it even further away, and we plan to make it like more really optimized for the high volume, high frequency data. We plan to rewrite some of the components in Rust. So we did a benchmarks for the ingestion framework that we have. So we did it on the NYC taxi data set, like 4 billion records. We were able to do like historical sync with a 580,000 RPS with a CDC performance of about 46,000. So from a lot of like other managed players in the market, we are around like almost 10 to 200 times faster for full load, or for CDC, we are almost 1.5 to 70 times faster. And Debezium, we are almost 40 times faster in full load and almost 3 times in CDC. So yeah, Arrow, I definitely want to talk Arrow a little bit. So what we realized is why don't we use Arrow to write into Iceberg, and also with the new feature being launched about ADBC, which is like an Arrow-based JDBC. So we are going to read the data in Arrow and then write it into Arrow in Iceberg. Now, for a lot of people who are wondering like, how is it better? So Arrow is like an in-memory columnar format, and we take the Arrow record batches and we can directly dump it into the Parquet without having to have a lot of serialization, deserialization overhead. So that's why it's really fast. It's also really memory efficient. And right now we use Arrow to write it into Iceberg. We dump all of that data into Parquets and just register those Parquets into Iceberg. But as a future roadmap, we are also planning to read data in Arrow itself. So we have designed the internal rolling data writer for Arrow. Yeah, I think the performance boost that Arrow gave us was like almost 1.5 times faster than the previous version of Oleg, and it gave us a lot of simpler architecture because we don't have to do the serialization, deserialization. We were using Java kind of APIs to dump the data previously. Now we are just simply using Arrow and Parquets, and then register the Parquets using the Java interface. Yeah, I think the future roadmap, we have definitely warehouses is being requested by the community a lot, because I would like to talk about the problem number 3. Like when organizations already have like a lot of data in their current existing pipelines, usually if you think about it, queries usually happen on a silver and the gold layer of the data in the medallion architecture. So a lot of people, what they're asking is they want to get the data from their silver and the gold layer into Iceberg, and they want to get away from the vendor lock-in kind of a free zone, right? So that they can now query using, let's say, something like DuckDB, using LLMs. So a lot of people actually, like one of a really interesting use cases, people are querying Iceberg tables in using DuckDB and LLMs. So this is one of the interesting use cases we can see. And also, that's the reason why we are adding warehouses as a source. And then table optimization, as I mentioned, this is in beta testing internally. We'll be launching it soon. Upcoming features like watermarking is something that is there. JSON flattening and variant types is something we are integrating with the integration of V3, and hard beating for avoiding the wall bloats and partition evolution is something that we do have in roadmap. Yeah, so we are contributing it back to community. We are contributing it back to Iceberg. We have contributed fan-out partitioning in Iceberg Go. We are also contributing a couple of bug fixes in Iceberg Java. Yeah, and also a lot of companies, a lot of data engineers, they are contributing it back to Oleg, or they're using Oleg in their staging productions whatsoever. We have gotten a lot of issues or Slack. We get a lot of people from these companies to ask questions. Yeah, so I'm happy to take any questions. You can scan the QR codes. Would love to have any questions if you have. Yeah, please.
Do you support the first append on Iceberg? So the first append is, instead of creating a new manifest list, we just append at the end of a manifest list. Is it something you can do? Or
yes.
You create it? Okay.
Yeah.
Yeah, but because it boosts a lot of performance.
Yeah. Especially like we now are introducing sources like Kafka and S3, because they are mostly like append first sources. So I think, yeah, we definitely do support that. We still use like Java APIs under the hood to do that, and I think Java supports that well.
And sorry, last question. Are you considering to have connectors to leverage existing integration framework like NiFi, Camel, or stuff like that? Because thanks to that, you can open the number of. I mean, Camel, for instance, we have, as far as I remember, 400 connectors that exist. So instead of reinventing for you before to create a bunch of connectors, you can leverage what is provided by this kind of products.
I think the overall thought process is that we want to focus on the volume problem here. So I think the connectors for, let's say, Salesforce or something like any SaaS tools out there, this is pretty much being solved by a lot of good tools out there like Airbyte connectors and a lot of good things out there. And we want to focus on the problem where it gets really hard for the people. And that's when it comes to the volume. Like we have seen a lot of companies, they struggle with actually like a terabyte, anything that goes beyond a couple of terabytes, they struggle a lot.
Yeah. And so in this regard, for instance, you look at Absolver, they use a very specific approach where they add extra metadata for their own use cases of ingestion.
Yep.
And then they are able to do maintenance in advance because they know exactly what happens during the ingestion. Is it something you do as a output storing extra metadata?
We got inspired by Absolver. Like we like the way the approach that they took, and I think we are something which we are already doing something to achieve something like exactly once, right?
Okay.
But we are also planning to do that for the compaction as well. That's the reason why we forked Amaro, and we want to like make it really tightly coupled so that we can actually pass some of that information to Amaro and back.
That makes sense.
Yeah. Yeah, please.
Yeah, you mentioned that you want to rewrite some parts in Rust. What parts do you want to rewrite and why? I know exactly that in Java arrow there's a problem of converting arrow to Parquet. So
I think so. The part where we would like to write specifically is the part where we are doing the compaction. So especially like some level of the medium or the full compactions, I think that that can benefit a lot if we convert that to Rust. So and I mean it's mostly like a compute heavy process. So Rust might give it like a 3 to 5x more efficiency compared to the normal Java one. Yeah. So that's in the roadmap right now. Like definitely like to have a lot of contributors to contribute around that side. It's just like it's the feature is in like a beta testing. We have just forked Amaro and we have started working on it like a couple of months back. Yeah, please.
Are you considering a DBC as connectors?
Sorry.
Arrow database connectivity.
Yes. So I have mentioned that in one of my slides.
Yeah, I missed that.
So we recently we are going to have a like a webinar with Matt in the Iceberg Summit. So we are definitely thinking of ADBC in for a couple of databases for sure, because it gives like end-to-end arrow, right? So yeah, I think we are definitely.
Especially for BigQuery, you have ADBC,
yes.
and so you can consume directly using ADBC to arrow vectors, and then you can push to Iceberg like that.
Yeah, and also a couple of other interesting use cases that people have talked to us is like something like a single message transform.
Yeah.
So if you have it in the arrow record batch, you can actually use something like an internal DuckDB and then do like SMTs on top of that. So basic.
With Matt and David on that.
Oh, okay. Yeah, please.
How easy is it to control in terms of the ingestion? So to optimize in terms of you're also optimizing control. You have lots of small files, but you might also want to optimize the contents in terms of you want the minimaxes to be kind of reasonable, close enough for you, like not that in maxing. Where is that done, if anywhere? So
for now, it's not done, being honest, because I think it's just the starting of this compaction as a feature that we are launching, the table optimization part. But I think we definitely have plans on doing some level of sampling, because we read from the databases. Today, the way we calculate like the average row sizes and the stuff like that is we sample from the databases and then we decide like what should be the optimal size for a chunk. And in the same way, if we can also do some level of sampling and decide the min max and some other, we can translate that information from the ingestion sources into the compaction. That makes something of a bit more sense. So today we are not doing it, but we definitely, it's a good idea. We can actually think about this as well.
I would say, Shubham, thank you very much.
Thank you. Oh, sorry.
Guys, you made it. It's almost 9 p.m. Thank you very much for your attention and for all questions. And I hope it was kind of fun to learn more about Iceberg, about data. And now we have a couple of minutes still here to have a networking until we'll be kicked out, Lorena, right? Okay, so we have 30 minutes to have a network. And see you next time all on June 4th at Fresher.
Thank you. Thank you. So we kind of like, we internally had a thought like, how about if we donate it to the foundation? We are still discussing this